Our next presentation is Nonstationarity in flood frequency in the midwestern United States. And the presenter is Dr. Tom Over. He is a research hydrology with the USGS Center, Central Midwest Water Science Center in the Urbana, Illinois office. Tom has worked in this center, formerly the Illinois Water Service Center, since 2001. He's currently leading or assisting in projects investigating methods for the prediction of peak and continuous stream flows in ungauged basins, determining the uncertainty of measure and model stream flows, and estimating the effects of climate variation and urbanization on peak stream flows. Immediately prior to his appointment with the USGS, he was a professor of civil engineering and began his career as a consultant civil engineer in California, helping to develop the first FEMA flood insurance rate maps for San Diego County, among other projects. Dr. O?
I got you, man. This is you right here? That's me. Sweet. All right, there you go. Thanks a lot.
Well, thank you, everybody. Good to be here. As Roberto said, I'm Tom Over from USGS. Wanted to make sure to note on the cover slide here that this is a transportation pooled fund program project, and it's kind of a progress report because we're just in the middle, and we have mainly the first phase, mostly but not completely done. We've especially the federal agency people making our jokes about our disclaimers. We don't have to usually have to worry about lawyers, I guess, because we're not a regulatory agency. But to get our presentations or reports approved is usually a lot of hoops. So you'll see there's this preliminary, and things could change. It's not yet final, but it's final. With that disclaimer, I am allowed to show it to you. So. This project is, like the title says, in the U.S. Midwest. It has these 9 states that are outlined here, and they're listed down the left. Most of the cooperators are state DOTs. You're probably all familiar with how these pooled fund programs work, but the nice thing is, that other agencies other than DOTs could pitch in funds, and the USGS could too, and there's 4 USGS centers. I should say before I skip along, we are grateful for those agencies that have pitched in, and then there's 4 USGS water science centers that are involved. They're these days in our area anyway, multi-state. Many of you may know we used to always be state-based, but we've combined across states, and so there's at least a couple people from each one of these centers who's heavily involved in this study. I'm by no means the the lead or whatever. I'm the person who stuck up his hand and said, I like the NHEC conference, it's a good conference, and I'd like to go present here. So that's why you have me. I did also, and you'll probably see this in the presentation. I was kind of the leader on putting together and analyzing the climate data that we used. So. I didn't develop it, but so as you know, peak flow frequency analysis is quite critical in water resources management. And Bulletin 17C, which is the latest federal guidelines, the guidelines are basically set up to assume stationarity. It does allow for the idea that climate is changing, and you're encouraged to incorporate that if you have good evidence for your adjustment, and also that you should check for watershed changes when you look at your peak flow records. So we here we are. So that's where you're left, right? So we're trying to come in there and say, well, can we help, look at what changes are observed, and both in the climatic variability and in the watershed changes. And so this project has 5 phases. First, to look at the peak stream flow data itself, and primarily the changes in the magnitude. But we're going to look at both the trends, the change points, and the timing during the year, so in other words, the seasonality, and then how those relate to climate metrics. The second one is to focus on the seasonality, because that's useful in knowing what your causes of your floods are. If it's a spring flood, you're often thinking it's probably related to, or especially early spring, a snow melt or a rain on snow event, and if it's in the middle of summer, probably not, and so on. So that has a lot of useful information even without your climate data behind it. The third is getting into the land use, the effect of urbanization. The fourth, effective agricultural drainage on stream flow. And the fifth, then try to pull it all together to say, how can we incorporate these insights into the design process. So today I'm just I'm going to focus on that first phase, looking at the peak stream flow trends and some of those other aspects, and just for the preview, as far as what what will really come out at the end, is there'll be a large report with 1 chapter per state, because it was decided that that's the way the cooperators probably want to have their information focused on their own state. So that's how the results will finally be presented. Then for the analysis used, we have 4 periods. We look at 4 different periods: a 100-year period, a 75-year period, a 50-year period, and a 30-year period. Those all, as you can see, end in 2020, so that you're pulling the data up to the current time, because that's of course the most relevant for the future. And you can see the number of stations involved increases as you go along, and so there are 841 total stations included, and these were sorted out to remove stations that didn't have relatively complete records or that were strongly affected by regulation. So, and that made this map of stations. There's some stations in some outside of some of the states, and those are on rivers that flow into those states. So those are usually included because they inform you about rivers that are in the state of concern. Just for kind of, like I kind of warned you, I would emphasize the climatic side. To give a little background here on that, I really always, ever since I saw this paper, really liked it. It looks at clusters of change points in stream flow. Now, so these aren't peaks directly, but annual stream flow. And so spatial clusters and the year at which they occurred. You probably can't read the numbers of the years, but starting at the upper left, those aren't the clusters, those are just the trends. So in all these, the blue is upward and red is downward. So you can see in our study area, yeah, that's how this happens, huh? You try to hit the pointer and you hit other things. Our area up here, that in the kind of the southeast side, it's of the study area, where like Illinois and Illinois, Iowa, and that part, a lot of upward trends. Then the Red River Valley, the North Valleys, you see a lot of upward, and then kind of the northeast part of the study, either no trend, which is black, or a few down trends, and then the western part, again, a lot of no trends and then some down trends. So, and this pattern kind of, you'll see, actually continues through the whole talk. And then going to the clusters, you can see there were some upward clusters in Montana. Actually, this one's 46 and 63. Then there was this big area of upward trend, upward shift in flow around 1968. People have often, it's very famous in the literature, often said circa 1970. But that's, of course, when we have this larger perspective, that's only in the eastern part of our study area. And then in the last 25 years of this study, there's been, again, a downward shift out in Montana and a downward shift here in the kind of northeast part of the study, and then an additional upward shift more in the southeast, there in Illinois and Iowa. So, kind of, and I'm going to show maps like this all the way through, so, hopefully those patterns will be reinforcing that it'll, your mind will remember that from slide to slide. So when we did this streamflow analysis, we looked at, a whole slew of things really. We kind of analyzed this thing to death perhaps, but the main takeaway, the main things were, what are the trends in the mean or the quantiles? We looked at, how is the high flow changing, the high peak flows as opposed to the low peak flows. That's the trend in the quantiles. But the main thing I'll talk about today is the trend in the mean, where as if you were just fitting a regression to all the data. And then also the seasonality I'll touch on today. We also looked at some other, just kind of for the full background, what's going on in the daily stream flow and in the peaks over threshold. So for the trends in the mean, these are tested with what's called a Mann-Kendall test, which is a non-parametric test. And you can fit a slope in a non-parametric way, in other words, not using a least squares regression with this thing called a send slope, which is you take the median of all the data pairs to get a slope. And then there's a problem when you use, typically in a statistical test, you have this p-value, which is telling you the probability that the null hypothesis is false or is true. And then in trend tests, famously, so if we require that the p-value needs to be small, so you're really sure you have a trend, or you're really sure anyway the null hypothesis of no trend is false, you get a lot of false negatives. So, if you have trend data that you know is trendy and you test it this way, you get a lot of times you say, well, I'm not sure that I have a trend. But really you did, because that's the way you synthesized your data. So to avoid that, we use something called we're going to use something called a likelihood, where it's 1 minus the p-value over 2. And in this case, when it's, do these all together here, if that's 85 to 100%, then we're going to say it's likely, and the slope will tell us whether it's upward or downward. If it's 70 to 85%, that's somewhat likely, or if it's under 70%, we'll say it's about as likely as not. So that's the kind of language I'm going to be using. And just for one example here, in this stream gauge in Illinois, seems by eye that it's very likely that there's a strong trend here. In fact, the p-value is negligible relative to 0.001, and so this is likely upward. So that that would be an easy example. So here's the maps of the results. So the maps I produced are going to look like this, where we'll have the 100-year in the upper left, this 100-year trend period, not the 100-year flood, but the 100-year trend period in the upper left, 75 here, 50 here, and 30 there. And we don't really have a lot of data, as you can see, in the 100-year trend. So, that's going to be locally important if you're, studying that state, potentially, like Illinois has a number. But, for today, when I want to look at spatial patterns, I'll probably start up here at the 75. And as I was saying, there's a tendency to see, upward. So these will all be blue or upward, red or downward. The southeast area, again, is usually blue, usually upward trends. You get some areas like in the 50-year here in the northeast part, you're getting downward trends. And in the west, downward trends a lot. Although there's also peppering, right, of red in these other ones, where, again, we when you're thinking, that previous slide was only climate, right? So no land use effects. So, some of the reasons we'd have to, drill down and look at these. Why are we have these peppered exceptions in there? But, the general trend is similar, where it's upward in the southeast. And then the numbers in these tables that tell you, like in this slide, 73% is upward, likely upward or somewhat likely upward, and 21% likely downward or somewhat likely downward. That's in part, dominated by the regions where there are more gauges. So it's not necessarily a spatial average, but a, gauge-based average. And then I just want to touch on the streamflow timing just for a minute. Now this is a density fit to the month of the year in which the peak occurred. So at this gauge, most commonly they were in April. But if you look at it over time, this is going through the year, starting in the water year in October, November, and so on to September at the top. So this upwards fitting slope means that it was getting later in the year. So it started in mid-March, ended up in probably mid-April. And so we also applied that likelihood test to these trends. And actually so then the same set of maps applied to the seasonality trends. And actually the patterns are again fairly similar. And but in this case they have a different meaning, right? That upward means later, it tends to be going later in the year in that region. Downward tends to mean it's going earlier in the year, the peak's occurring earlier in the year. And so in this case, maybe you might think out here in, of course, on the western spine of Montana, you have in the Rockies. So this is going to be likely snowmelt related. So if you're having less snow and it's happening earlier, then if you have less snow and it is warmer, it'll melt off faster and it'll melt off sooner. So then it's not surprising that it's happening earlier. So getting into what the climate data that we use now, what we're going to end up with is a model-based, it's a simple water balance model, but a model-based estimate of the stream flow at a monthly time step. The idea to sort of focus on that rather than the precipitation and temperature is that there's storages, of course, in your watersheds. There's the snowpack and there's the soil storage, or the groundwater. The soil storage is a very complicated thing, of course, in a watershed, but in this model it's just a soil bucket. So the changes that occur through the climate are mediated by those storages. So we're hoping to get some kind of a hydrologically effective effect of the climate changes by running it through the model to get its effect on the stream flow. We will look separately at the temperature and precipitation as well. And so, like any rainfall runoff model, this is forced by temperature and precipitation, and it predicts your basic variables. The splits the precipitation into rainfall and snowfall depending on temperature. It predicts potential and actual evapotranspiration, that soil moisture storage I was talking about, the snowpack, and then the runoff, and it's a gridded model, so then we aggregate over all the grid points inside of the watershed to get a stream flow for that relates to that gauge. And a reminder that there's no land use change in this. So this kind of modeling, is only showing the effect of the climate. And this is a model that's developed by these Greg McCabe and Dave Wallach, who are also USGS people, and they for another project they were applying this from 1900 to 2020, and they just happened to have it ready just at the time we needed it. So they just gave us the data. So that worked out really well for our project. And the other sort of disclaimer on this is that, of course, this is a monthly time step, and so it doesn't really model the peaks directly. So looking at some of the climate data then, here's the precipitation. And so again, here blue is upward and red is downward. So most of the time, again, same kind of pattern. The southeast, it's always increasing. So the precip is increasing in the south, and then the northeast was sort of our stream flow as far as the eastern side. The northeast had the downtrends. Now here the downtrends seem to have shifted a little bit to the west, so the precip isn't really explaining, well, there's not much trend in the northeast part of the study area. We do see here in the 50-year some downward trends in the precip out there in western Montana that corresponds to downward trends in the peak flows. So moving on to temperature, here blue, although you might not think of it physically that way, blue here means again upward. So now this is almost universal. It has been getting warmer over the whole study area at all the time periods, except in the last 30 years here in the not the extreme west but the middle west of the study period is kind of flat. So hydrologically, what that's doing is, well, probably reducing the amount of precip that happens as snow, and it's also the increasing temperatures are also increasing the amount of your potential evapotranspiration, which means if you have the soil moisture available, it's also increasing the actual evapotranspiration. So there's kind of an so the increase in precip is offset at in a certain sense by the increasing ET. And then those modeled streamflow trends or runoff trends that I was saying was, really what we're going to mainly focus on. You'll see they're still mostly positive in the southeast, as have we've seen in all the plots. We are getting some negative trends up here where the effect of the ET has overcome the effect of the precip increases, and again we're seeing the decreases in stream flow out in the mountains of Montana. And then just to, in case you didn't remember how the patterns looked, here's the peak flow trends again. So, roughly, I'm saying, if you believe me, the spatial patterns are basically the same, but you see this peppering of some downtrends in the peaks in areas that the climate would say should be mostly upward. So whether that's due to land use or there's some other local factor, we need to drill down and look at. Doing a cross comparison again, just for the 50-year, I've highlighted up here in the left, the peak flow trends are in the upper left, and I've highlighted this area. There's kind of a dipole in the Dakotas, kind of the central Dakotas, and then eastern Montana, where the peak flow trends are down, and then it's upward in the east here, which this is kind of the Red River in the North Valley, but yet the climate data is sort of our sore thumb of this process. The climate data, the runoff data doesn't really pick up that dipole, the precipitation doesn't really pick that up, and the temperature, okay, the temperature is going up moderately there. So, there's something more needs to be done to understand what's going on in that region. So we haven't explained everything, but maybe I shouldn't highlight the part where it didn't work, but that's what jumped out at me. So that's what I'm saying. But there are all these areas where runoff is up here, precipitation's up here, most of the peaks are up here, and I'm saying there's local factors probably to look at for the peppering of the downtrends. One other, how am I doing? Okay. Next to last slide, although this is a busy one. One other way to try to, rather than, waving my pointer around at spatial patterns and hoping you believe me, a sort of, numerical way to collect that data together is to take all the peak flow trends and then plot them against all the climate trends of different kinds, like the stream flow trends, the precip trends, and the AET trend, the actual ET trends, and then test which one of those has the strongest correlation with the peak flow trends. So that's what we did, and these are the selected climate variables here are the ones with the most statistically significant correlations for the 30-year trend period. But I'm also showing you the results from the 75, the 50, and the 30. And we kind of cheated here at the top, which is we included our observed stream flow. So not the peaks, but the daily stream flow, aggregated up to annual or monthly. So if you have the daily stream flow, which we don't in the future, of course, you can do pretty well. You're getting like a 50% correlation. If you look at the month, if you look at the trend in the month where the stream flow is the maximum, that really helps you compared to the annual stream flow. If we do the same thing for the modeled stream flow, which of course includes none of the land use change, right? That observed stream flow includes all kinds of information that our simple water balance model does not include. It's still very significant, but it's not as high as the observed. And then the monthly versus the annual doesn't also gain you as much. And then the precip is almost as good. And then negative correlations come from the factors that take away stream flow, like the actual ET or the potential ET. And then the snowfall over precip is inconsistent. It doesn't really have an obvious physical meaning, so it's not surprising that the result is inconsistent. So that one I've grayed out, is not useful. So that's the summary of the climate interpretation of our results. And to summarize the whole thing, the trends in peak flows and in timing are common in our peak flow time series across our 4 different time periods. The magnitude trends are often associated with trends in climate, but that connection isn't always strong, and that may be in part because of land use effects and because the model could predict them better if it was not at a monthly time scale instead of perhaps a daily. Detailed results, as I was saying, will be presented by state. There'll be a detailed chapter for each state. We haven't looked at land use change yet, but that's considered in next phases, and then incorporating these results into design type of ideas will be done in our last phase. So thank you for your attention.
Question?
I was noticing that you mentioned the peppering in the peak stream flow events, that often you'd have adjacent gauges that one had an uptrend and one had a downtrend. And you mentioned land use as a possible contributor to that. I was also wondering if catchment size contributes to it, in that smaller catchments have a shorter response and the peak flows are coming from shorter, intense events, whereas larger catchments, the peak flows are coming from longer duration events. Could that be confounding the results then?
Yeah, the question was, could catchment size be affecting these trends or be a general explanatory factor? And yes, I agree that that could. If we've done a little bit of work like where the smaller, to show as you would expect that the smaller basins are more commonly rainfall based, and then in the areas where you have some snowmelt oriented and some rain, that so if those are happening, if the climatic changes are affecting those two processes differently, then you could have peak trends going in different directions depending on size. Yeah.
Does this research indicate which time frame is most representative of how we should look into the future? Do you feel that 30 years is representative of where we're going?
That's not a question I really have an answer for at this point. It depends. In some of these areas they've seen kind of a shift from a dry to a wet climate, and that may have happened over longer than a 30-year time span. And so, you know, it's very site-specific in that sense. So, you know, we have to kind of, that's why to look at all of the history and see site-specifically what seems to be going on. And then, you know, predicting the future, of course, is a challenge for anybody. So, yeah, there's not as, I guess that was a way of saying, there's not an answer, there's not a decision made on that in a general sense. Yeah, definitely.
Thank you.